Hey, what's going on, guys? Komakikins here. I'd like to welcome you all to this 6502 assembly programming crash course, and the purpose of this crash course is to teach you how to think in assembly programming language. And the way of thinking in assembly programming language is really agnostic from the particular processor we're talking about. So assembly generally is different from the high-level languages. But instead of just directly diving into the instructions, I'd like to try to explain how it's different. And because if you don't understand this difference and just going straight into the instructions, it seems and it feels like lots of unnecessary complications arising, and you might be thinking like, why the heck I need to do this in this way? But these complications are determined by the nature of the processor, and you really need to understand how exactly the computations are working underneath, because only in that case it starts making perfect sense why exactly the instruction set for a current given particular processor is done as it's done and how to use it. And once you get that understanding of how these internal parts of the processor are working in cooperation with each other, how they work together. In that case, it really starts getting intuitive. And once it started getting intuitive, from there on, you can actually feel absolutely comfortable referencing the documentation and looking for a specific things that you want to perform. And you know what things you want to perform. You're starting thinking in the right direction. So you need what are you looking for, and you just started figuring out like where to start looking for the information in order to make what you want to do. Okay, so the path gets very clear. And the biggest issue with assembly is not the instructions, and it's not like that say 6502 is different from x86 or something like that. The problem is the lack of this understanding, like the core difference between the high-level languages and assembly. So the very first and the introductional part of this crash course is going to be a very simple visual example of the difference, how high-level languages and assembly language, 6502 in particular in this case, kind of operates. And as soon as we get that difference, we'll then go to the basic instruction sets, addressing modes, loops, and branching, and flags as well, because branching is very dependent on the flags. And then we'll have a look at the function calls, and at the very last, a bit of a bytes declaration, which is specific to this environment that we're going to be writing our code in. And by the way, I highly recommend to watch the previous video in this series covering what this environment is. So this is known as JavaScript 6502 assembler and simulator. I've been covering how it works in particular, so where what bytes does map to the memory map, to the video memory, where we can get the ASCII character input, the random number feed, the random number feed, not the seed, but the feed. Yeah, and generally a bit of a history of this environment and why it's so cool for learning purposes. So if you didn't watch that video, I highly recommend to go in the description below this one, find a link for a playlist, get there and watch the very first video. Okay, so without further ado, we can actually start. So if you're ready, buckle up and we begin. So if we think about programming like from the high-level programming languages perspective, and let's consider the simple addition. So let's say like in JavaScript, for instance, right? We have variable A is equal to 2, and then we have variable B is equal to 3, and then we have the variable C, and we want to say that C is equal A plus B. So it's clear, it's very simple, and nothing special here. But when it comes to assembly, it stops being that clear and stops. So you can't do this in assembly directly, because if we try to understand what's going on under the hood, right? Actually, the variables are locations in memory. So we need to have one memory address containing the value of A, another memory address containing the value of 3, and then we want to put the result into the third memory location. However, the hardware works that way, and well, this is specific to 6502, but this is also true to x86 as well. that we can't perform operations on the values of the memory locations directly. Instead, we need to use so-called processor registers and general purpose registers in particular in order to load the data in there into the registers, then perform some computations, and then we can output the data to the certain memory locations. However, quite often it happens that we don't even need to, so if this is a small operation, that it might happen that we don't even need to put that, the result into the certain memory location, so we can just carry that in the register along the way. So sometimes, well, depending on the number of registers, well, obviously with only 3 registers in 6502 processor, it's not the case in most cases, but in x86 that might be the case. So it might happen that instead of having a like separate variable for some sort of a parameter, you may use just a register for that purpose. Especially bear in mind that the size of the registers, if that kind of allows that, that's the case. Again, like, it's not exactly regards to 6502, but it's very important from this perspective of how to think in assembly language. So sometimes registers might be treated as the extra variables, and they are kind of like a super global variables because they are located on the processor and not in the memory. And that's the reason why referencing the value in the register is much faster as opposed to referencing the value in the memory. And also, again, like for 6502 in particular, it's very essential to have, let's say, for arithmetical operations. So let's say we want to make it an addition. We can only add the value if to the one that is available in the accumulator register. So let's say in x86 we can add to whatever register, but in 6502 we can add only to the A register, the accumulator register. Okay, so now without actually diving into the instructions, so the instruction in the next part in this crash course. So now I just try to write a program that does this sort of a thing in a 6502 assembly, just to give you an idea, like the general idea, like conceptually, what happens conceptually, and then when it gets clear what happens conceptually, then we'll get into the details of the most basic instructions. And in that case, these instructions will start making perfect sense of why they are like made like that. So why actually to have that many instructions and so on. So the instructions themselves would get crystal clear as soon as you realize the conceptual, like the concept of how this entire computation works. Okay, so I just we can use the semicolon symbol to declare the commentaries, right? So so we know that in order to perform the addition, we need to have at least one value in the register, but another value can be taken from the memory. So without getting into the details of addressing modes, which is also the topic of this crash course, but it's going to be covered a little bit further on, we can do the following things. So we can just load the value into the A register, and we want to load the value of this. If we want to load the value, I'm using this hash symbol, and then $sign stands for hexadecimal numbers. So it's, if you're not used to hexadecimals, you really need to learn them, because this entire 6502 assembly relies on only hexadecimal numbers. Well, actually, this environment allows to deal with the decimals, but I highly discourage you guys from doing this, because when it comes to the real assembler and like programming for real hardware like NES or Commodore 64, you really would be forced to work with the hexadecimal numbers. So just better to kickstart with the hexadecimal numbers from scratch. So the $sign says that the next number is hexadecimal, and it's a good practice to, let's say, not doing like this, but 0 to, so each digit represent a nibble of a byte, and two digits, like 2 nibbles, represent an entire byte. So nibble is 4-bit, byte is 8-bit. So 2 digits, 1 digit is 4-bit, another digit is 4-bit, and together they are 8-bit, which is 1 byte. All right, so this lets us to load the first value into the register A. And now we want to store this to memory. So if we want to represent exactly what we have in this code, so we need to take some address that is going to be treated as the A. So let's take the verb first. So STA stands for set set the value from accumulator to whatever memory location, and let's specify the direct memory location of 0000. We'll now see this in the monitor during the debugging, right? And then, so here, so these two lines actually does this stuff. So so variable A is, so we will think that variable A is going to be the address, this address, okay? And then the variable B is going to be in the next byte, in the next cell. So again, like I'm loading the value of 3 now, and then I say STA, and in this case 0001, right? So at this point the initialization is done, and let's assemble the code. So we got this successful assemble. This is the memory map. So we have the random access memory starting from 0, and this is the length of how many bytes we can see. This you can change this and change this as well if you want to inspect a different part of the memory, right? So now let's turn on the debugger to see what happens exactly. So in step 1, so the very first thing, we just loaded the value of 2 to the accumulator register. So okay, it's probably time to say that we have 3 general purpose registers. Oh, okay, let's cover this a little bit later. So we just loaded the value of 2 to A register, all right? And then watch here. So the next step, we put the whatever value we have in the A register to the memory address of 0000, which is here, right? And then the next step, we do load the value of 3 into the A register, okay? And the next step, we actually set this to the next cell, to the next memory cell, to the next bytes, with the address of 0001. Okay, and now we need to perform the calculation, and the only command that is available for 6502 for addition is ADC, which stands for add with carry flag. And we see, so we can add an instant value to whatever we have in the A register, but we want to, but actually here we're not dealing with the instant values, but with the variables. So we can also do that as well. So in that case, we can actually load the value from memory. So we can add the value from memory to the A register. And also, if we have a look at this LDA, so here it also is, so what we've used so far, we just uploaded the immediate data. So we were working with the immediate data like 2 and 3, and the next step we're going to be doing the uploading of the data from the memory. So the syntax gets a little bit different, so let me just cover that. Well, let me just better demonstrate you this. So if I say LDA, and now I'm not specifying the value, the instant value, but instead I'm specifying the memory address to load from. And in this case, we have 00, which means that the value at 00 is going to be uploaded to this A register. So if we assemble and run, then after all the steps has been completed, we have 2 in the register A. So I hope this is clear. And then we want to say add with carry. Carry stands for carry flag. It's used if we exhaust the 8-bit register, like if the number is going to be greater than FF or 255 in decimal. In that case, the carry flag would be set. That's how we know that we just have this. We've exhausted the amount of bits that the register is capable of storing, but that's a bit different story. So add with carry, and now we want to add the location of memory 01. And after all of this stuff happens, A register should be containing the value of 5. So let's have a look if that is so, and this is so. And then the very last thing, we want to store the result to the variable C. So we can simply say STA and to the memory cell 02. We want to store whatever in the A register and run. And now we have A is equal to 2, which is here, B is equal to 3, which is here, and C is equal to like a plus b, and it's equal to 5. So in order to come up with this sort of a program, like from the high level languages, programming languages perspective, this is what we need to do in 6502 assembly. Okay, so now you've seen that all the like the matter of coding in assembly is all the matter of referencing the registers and the memory locations and interact between them. So the entire programming in assembly is just a matter of like register and memory interaction. So all the instructions that we have starting from now actually relies on this very thing. So if you have a more complicated logic than this, you may also need to use the X and Y registers, which are called, well, now it's time to cover the registers. I'll do this just run in a moment. So if it's not enough, if one register is not enough, you have this additional ones, and also you have the flags that in most cases they're used for like as conditions for branching. Okay, so the registers, right? I'm just referencing my plan there. So we have 3 general purpose registers. So A is the accumulator, X, Y are called the index registers. So how different are they? So accumulator allows to perform arithmetical operations, while index registers don't. Well, for comparison, in x86, all the registers, all the general purpose registers, allow to perform arithmetical operations on them, which is very handy, makes life easier. But the hardcore 6502 doesn't, and this what makes it so fun, and this what helps to improve your thinking in assembly. So one of the most common use cases for X and Y registers is for indirect memory addressing, which we're about to cover later on. So if we want to increment so you want to store some value, not to the fixed memory address, but to the incrementally updated one. In that case, X and Y are getting incredibly useful, and we'll have a look at that, I promise. So 3 general purpose registers: the stack pointer, which was covered in the previous video, so have a look, as well as the program counter. So program counter is literally the pointer that points to the next instruction in the source code to execute. Well, not this mnemonics obviously, but actually the actual instructions that the opcodes with the data followed by. So this one, and so on. And the flags again, and the flags would get affected by some instructions, and the documentation always clearly states what kind of flags can be affected if the certain instruction occurs. So it's impossible to remember everything. So if you are interested in figuring out what flag gets occurred, you can always see this in the documentation for every single instruction. Okay, so yeah, now let's have a look at the most basic instructions that you would most likely need in order to write something useful in 6502 assembly. So we've already had a look at loading the value to A and setting the value, add the A register to the memory, and just like this, we can also do the same with the X and the Y registers. So let's say if I say LDX, so stands for, so we can load and set to X and Y, and where is the LD? Yeah, LD, LDA, LDX, and LDY. So LDX does the same that LDI, but it loads data to X register. LDY loads data to Y register. STA sets data from A register to memory, STX from X register to memory, STY from Y register to memory. Let's quickly have a look how this works. So let's say I want to load the immediate value into the LDX. Let's say hexadecimal 10, which is decimal 16, for instance, and I want to say STX and say 0, 0. Let's put it into the very first one. So this is what happens. So we did initialize the LDX, the X register, with number of 10. So this is seen here, and then we put this value, the value of X, to this absolute memory address, and here we have this. All right. if we do the same with the Y register, then we have now the Y register containing the value, and still just now we put in the value at the register Y to the very first memory cell, to the address 0000 hexadecimal. Okay, so also a part of this, so this load and save instructions is something similar to the methods like set and get that you have in the object-oriented programming. But also we have useful instructions to transfer the values between the registers. So let's say I want to load the value of 10 to register A, and now I can actually transfer this value to either register Y, or X to register X, or to register Y. So let's say we have this TAX, transfer A to X, and TAY, transfer A to Y, right? So TAX, and this is the 1-byte instruction. So if I assemble, run, and see, like first we load the value to A register, and then the next instruction transfers this value to X register. Okay, if we also do TAY, in this case we also have the Y register being initialized, and it works on the contrary as well, so we can transfer the value from X register and from Y register back to A register. So for instance, let's say LDX, let's say 2, and LDY, let's say 3, and now transfer from X to A, and then transfer from Y to A. And here we'll use a debugger. So first we have 2 being initialized, so register X now has the value of 2 after this operation. Then we did initialize the register Y as well, and now the next step, so we transfer the value from the register X to 02 hexadecimal to register A, and it is, and the next step we transfer from register Y to register A. Okay, so I hope this is very clear and self-explanatory. Also, we can increment the values of X and Y registers, but unfortunately not the A register. But as far as A register, we can perform the arithmetical operations. That's not the big deal really. So we have this in X, in Y, which stands for increment X, increment Y, and inc is interesting because it allows to increment the memory, right? So let's have a look at the increments. All right, so for instance, here we want to say increment X, which would just increment X by 1, and let's make it twice. So we can also have a look at the decrement. So it should be what a sec, D, yeah. So decrements the memory, DEX decrements the X register, the value at X register, DEY decrements the value at the Y register. So like this, and then DEX, and then let's say increment Y, and decrement Y. Okay, assemble, and now let's go step by step. So loading the value 2 to the X register, then the next command would increment the value by 1, which it is, increment the value by 1, then decrement the value by 1. Okay, then we'll load the value to the Y register. Okay, increment the value by 1, increment the value by 1, decrement the value by 1. And now transferring whatever we have in X register, so 03 would come to A, okay, and then 04 would come to A. So transfer X to A, transfer Y to A. So hope this gives you an idea of how this internal interconnections between the registers is actually working, and yeah, and also just to demonstrate how it works incrementing the memory. So let's say we want to increment the very first memory address several times, and then decrement this as well. So let's assemble, and step with the debugger. So here we will have our value. So we just incremented the value in the memory, all right? Increment again, and now we'll decrement the value in the memory. So this is how it's working. So this is a very useful thing as well. Okay, I think, yeah, this is it regarding the most basic instructions. So if you want some more instructions, well, actually we can also have a look at the push and the pop, but I've been covering them in details in the previous videos. So I was actually explaining how the stack works. So yeah, we can say so we can just push the values to the stack. So push, where is the push? Yeah, push A pushes the A the value at the A register to the stack, and I believe that we can also push the value of X register to the stack and pull it back by using TSX, right? So let's quickly check this out. So let's say load the value of 10 to the A register, then oh my god, I forgot this, PHA. All right, so PHA push into stack. Now let's say LDA back to 0. Okay, and then we can pull this value back to A. So let's assemble and start with the debugger. So initializing the A, pushing this to stack. The stack pointer decrements by 1, which is really kind of like predictable, right? And then we reset the A, and then we pull the value back from stack. So this is how we can free the register for quite a bit of time and then just get the data back. And well, actually didn't yet test this, but this should work the same with this TSX to push the value of S to the stack. And or hold on a sec. Yeah, I'm sorry guys, I'm not crystal clear here, so let me just make a little experiment. So let's say LDX, let's see the value of 10 and TSX. So does it put on the stack, or does it affect the stack pointer? That's a very essential thing. Stack instructions. Oh yeah, this affects the stack pointer. Yeah, so it's not the same. Sorry. So now the stack pointer after this, the stack pointer should be equal to 10, I believe. Nope. Successfully. Okay. If not, then let's say LDX. Sorry guys, I just didn't test this yet. I didn't think to include this into the crash course, but it just happened that for some reason, yeah, we just stepped into this territory. So as far as we did step into this territory, let's have a look. And by the way, that's a good example of what you will be encountering. So when you're learning, when you're trying to figure out something that you don't know yet. So this is, I'm just showcasing the process of how I learned these things. Okay, so I assume that okay, so I think that this should be putting the value of 10 to the stack and then reset and then pull the value from the stack. But I'm not sure, so let's have a look at the debugger. Okay, so load 10 to stack. Well, this doesn't decrement the stack pointer for some reason. Oh, here is what it's doing, guys. Okay, actually, yeah, it does what it claims to. So it takes yeah, we can temporarily store. Okay, so this is why it's needed. We can temporarily store the value at the stack pointer to the X register. Okay, and then we, okay, all right, and yeah, so this is not the menu. This is not the matter of pushing and popping data. This is just the matter of preserving the value of the stack pointer. Okay, so that's how it works. So I've just learned a new thing, and now I can explain it. Okay, so let's start from the very beginning. So we can start from this. sort of a thing. So we preserve the stack value. Let's say we just push something to the stack, okay, and then we restore the stack value. And I try to explain how this can be used practically. So the very first thing, so initially stakes point it, it's not exactly FF, it's 01FF, if I'm not mistaken. That was covered in the previous video, so make sure to watch that. So TSX transfers the value of the stack pointer to, not the value at the stack pointer, but the value of the stack pointer to the X register. Okay, then say we make a push which decrements the stack. But let's say we pushed something and then we want to forget about that forever. So we want to restore the value of the stack pointer. In this case, the next instruction, so we're restoring back this the initial value of the stack pointer from the X register. So let's say you're making a function call and you're never going to return from that. So this is weird from the design perspective, but if you need this for some point, at some point, this might be useful. And yeah, I've seen this instruction for the very first in my life, and this is so cool. I'm impressed, guys. I'm really impressed. Okay, so now I hope it's clear with the most basic instructions, and we'll also have a look at the jump instructions and branching instructions, but in the context of looping and conditional, kind of like conditional operators. But first, let's have a look at one of the most essential thing in regards to 6502 assembly, and not only 6502, but whatever assembly as well, is the addressing modes. Okay, so okay, the Wikipedia article is not, it's not that great. So let's go to the STA set value. So STA, for instance, set the value of a register to the memory. Yeah, here it is. And here, well, I guess, yeah, it just has all the possible, well, almost all the possible, almost all the possible apart from immediate addressing modes. So let's have a look. So the very first, well, actually we can demonstrate immediate mode with the STA, so let's use the LDA for this. So let's say like, so what we've been doing so far, so we've been using an addressing mode in this operation. So sample run, we just put the value of 10 to the A register, but from the perspective of sorry guys, just was a bit distracted. So here we load an immediate data to the A register, and this is known as the immediate addressing mode. So this is what we've been covering so far. So in order to make sure that we're dealing with the immediate data, we need to use this hash symbol. So this tells us that the value, the immediate data, should be loaded, let's say, to here, to the A register. But in order to demonstrate the rest of addressing modes, I would be sticking to this STA to store the accumulator. So one of the most interesting thing, and this is 6502 specific thing, so-called zero page addressing mode. So what the zero page is? So the zero page is the first 256 bytes that you can address using only 8 bits, so 1 byte literally. And how it works internally from the hardware perspective. So it allows a very fast interaction with between the registers and the memory, and it's stated that the lack of the general purpose registers in 6502 processor is meant to be compensated by this zero page addressing mode. So this is a very specific feature to 6502 processor, which makes it really special. Okay, so in order to reference the zero page, it's like the absolute addressing but you can only define the 1 byte. So literally the absolute address, and what we've been doing so far. So let's say STA to the absolute. So now we just for STA we can do like this. It just gives an error. Okay, so for STA we just specify in this case the absolute address, and assemble and run, and we have down in this absolute address. However, if we specify only the first byte and assemble and run, the result is going to be absolutely the same. But what has changed is the addressing mode. So here we're using the zero page addressing mode, and doing this is faster from the hardware perspective, and it takes less bytes from the amount of bytes we need in order to save this. So this is the hex dump for this, and let's make it always on top. And let's say here, okay, assemble, run, and the hex dump. No, still okay. As well, first the opcode is different, and then we have just well, this doesn't matter, but we have just more bytes to store along with the instruction. It takes longer to process, and just takes more bytes to store the 6502 machine codes. So yeah, and if you want to think, so you can think of the zero page, the first 256 bytes, as the scope for the variables that your program needs to operate on. And again, like just for some specific calculations, so it's kind of like a sort of a very quick lookup for processors. So again, like just three general purpose registers, but 256 bytes of the memory, very close. So from the very beginning, we're close to, I don't know, from the bus perspective probably. Yeah, it's very close. So it takes very little time to execute this. So executing this is faster than executing this. Okay, so hope this is clear. And let's go further on. So the zero pages. Okay. Also, what is very cool that we can use for this is specific only for the zero pages. So if we want to use the zero page address plus the offset, we can do this the following way. So let's say we load the immediate value of 01 to the X register, and here we also specify the X register. In this case, assemble and run. You select this stored not in the 00, but at the 00 plus the offset of X, which is equal to 1. All right. So I hope this is clear. So this can be done in the iterative mode, which is really cool. Then the absolute addressing that we've been covering so far. So here is the absolute addressing mode. It also, here we can also add the X offset for an absolute addressing mode, which works the same. But also here for absolute addressing mode, for setting the accumulator, we can also use, let's say 2. Okay. All right. So here we can also use Y, and in this case we will print 10 here. So the offset of 2. So assemble, run, and we get it, right? So this is what happens to the absolute addresses. Okay, now we're coming to the most interesting ones. Sorry guys, my cats are going crazy from time to time. Okay, so now the most interesting addressing mode is the indirect one, and indirect always uses the either X or Y offset, and the syntax is different. Well, to be honest, I have no idea why the syntax is different, but because the opcodes are just the different opcodes, but could be the same syntax. But I don't know, for some reason it's different. So in order to demonstrate this sort of a thing, I'm gonna provide a slightly different example. So let's write a new program printing drawing a pixel into the video memory. So let's consider 01 as the value for A register, and let's first try to store this at the hexadecimal 200, which is where the video memory starts, and this has been covered in the previous video. So if you want to know exactly how the environment we're working in works, make sure to watch that. That's very essential. And this allows us to print a single pixel at the very first the very first pixel, so it starts from this. But how can we do, so let's say we want to make the pixel kind of scrolling down, right? So in that case, we need to, we could have been adding like the value of x in a loop, for instance. So let's say ldx and 0, 1, so symbol run. So now we have, well, actually to make it scrolling downwards, it should be 32 in decimal or 20 in hexadecimal. So here it's kind of like scrolling down, but the problem is then let's say x goes 40, okay, then x goes 60, and then it goes 80, okay, and what else? And then it can go, so the next one would be like this, but this is not going to fit into the register because, so by the way, now if I hit assemble and run, it should probably set the carry flag, or no, it's not, it's just, it doesn't even assemble because the instant value is just too big to get stored in the register, right? So the biggest one we can have is this one, right? But how can we, so let's say if we have this statically, it's okay, but if we want to keep this pixel moving down, we'll need to make some extra STA statements, but this may not be the best ever case. So what we can do instead, we can use so-called indirect addressing. So if I say LDA, so and 02, and if I store it at the 01, so I store the value of 2 here, and then 0002 is going to be the little endian based byte order for this absolute address that we're going to be referencing indirectly. So let's get rid of this for a while. So just assemble and let's run. So here we have this 02, right? And now if we want to use the indirect addressing, we need to give, so for x the syntax goes like this. We need to, so this parenthesis tells us that we are in the indirect addressing mode. So here, indirect addressing mode using x as the offset, and here indirect addressing mode using y as an offset, okay? So it points to the very first memory location, and it would fetch, it would use these 2 bytes to initialize the indirect address, and then it would add the offset of x. So like this, and let's say for now, let's say this to 0. So assemble and run. Okay, and now you see, like, we still have this pixel. However, it's the value to, now we can actually increment the value here. Okay, so for instance, a part of only, so we can increment as before this dx register, right? Sorry, 10 bytes successfully. What did I do wrong? Okay, just a bit wrong place for, so first let's initialize the dx, or otherwise it just doesn't work as expected. So symbol run. Okay, it's still for some reason, so if I don't do this, yeah, to be honest, I'm a little bit confused why the initializing of X register does affect, so it's STA starts right into, okay, if we make it 00, symbol run, 01, assemble run. Okay guys, yeah, I've now just figured out something that I probably missed during the preparation for this video. So in order to get the behavior actually wanted, we need to use the Y register, and yeah, this indirect X and indirect Y actually results in totally different behavior. I'm sorry, I didn't even realize that when I was preparing for this. So let's say we have 0, 0 in Y register, and again, like the syntax is like this, okay? So just assemble run, and here is the pixel, and now let's say we want to move it 1 down here. So it's the same as the previous example where we had an absolute address, but now the address is actually fetched from the memory. Now the cool thing about this is, let's say, so we can actually increment this value. So we can say not only like this, but also we can increment, for instance, 0, 1, right? And this would be 300, so it should jump somewhere lower, which it does, okay? So by accurately manipulating the absolute address, the physical address which is stored in the memory, and by accurately altering the value at the Y register, and if we will do this in a loop one day, in this case we will manage to make this kind of one tiny little pixel moving down. So the problem is, where we can move left and right in an easy way. That's because we don't exhaust the register value, so it doesn't go above the FF, which is 55 in decimal. But when it comes to downgrading this pixel, we actually do exhaust the offset, and so the logic how this should be working. So we should have like we need to be updating this one by one, okay? And then I mean, not one by one updating, like plus 20 is plus 32 in decimal. So we're adding this offset until we get to 80, okay? Until we get to 80, and so here let's still be okay. So well, actually, why is that? Oh, nope, we don't want to. Yeah, I just incremented the first member location. No, it's horribly run. So assemble run. Yeah, so we are here, and I'm wondering, is this gonna start actually? Is this gonna be here or not? No, it goes a bit further on. So yeah, some extra work is needed to calculate this offsets properly. I just wasn't really preparing for this because, you know, like just wanted to cover the very basics of this instructions and addressing modes, and I wasn't really focused on writing some real programs for this video. That's going to be the topic of the following videos, hopefully coming soon. Okay, so I hope this is clear in regards to addressing modes. Oh, okay, yeah, and one more thing. So the one that, to be honest, I don't really understand how we can use that, but just to demonstrate what we had been up with already. So I'm not sure why it works this way. So let's start with the debugger. So loading 2 to A register, storing it in the memory location 01, then loading 800s to the X register, and then again, okay, loading 1, and then, well, for some reason it stores this 1 here, and to be honest, I have no idea why this is happening. So guys, in regards to this memory addressing modes, so indirect with X, well, I'm sorry, but I have no idea what this does and how we can use it, but I just didn't find a practical need for that. And if anyone knows this, how to use this addressing mode, and why is this needed, please kindly let me know, because I just thought that they are the same, but it turned out that they are not the same. Okay, so what else? Now let's have a look at the loops. So if we have a label, it might not be called loop, it might called be like label or whatever. And then we may do something here, right? And then we can let's say we can load the value to the A register, like 0, 1. Then we can load it back to like 0, for instance. Or even better, yeah, it's even better. Let's just increment the memory at location 0, 0, and unconditional jump back to label. All right, so symbol, and now let's use the debugger. So now it should be incrementing the value 1 by 1, probably until it gets I'm not sure, is this going to be wrapping around or not, so let's have a look. I'm just wondering what's going to happen after FF is going to be encountered. Yeah, so probably let's set this to, so let's say load a let's say F0 and then set to 0, 0, okay, and symbol, and okay, so we have this F0, and just wondering what's gonna happen after FF, and it wraps around. Okay, so it wraps around, and then we go again, and yeah, and it doesn't even set any flags for some reason. Well, maybe it doesn't have to. So if we have any doubts, we can just go back to the documentation and have a look at this inc, and yeah, it doesn't affect any flags. So yeah, if we go like above the value of byte, we can know that. So if we need to keep track of that, we need to explicitly implement that as well. Okay, so well, I hope this is clear in regards to loops, and now let's have a look at branching. Okay, so the branching relies on processor flags. So before actually using the branching, we need to figure out what command in particular affects the flags and what flags in particular, and that's the compare command. So we have compare, compare x, and compare y, which compares a, x, or y registers with the specific either instant value or zero page value, the zero page address, or absolute for x and y. This is it for a register. It contains the offsets as well for absolute plus the offset, and indirect plus the offset as well. But anyway, it affects the flags N, Z, and C. So what this means: the negative flag, the zero flag, and the carry flag. And these are three most essential flags. You need to exactly have an idea of how they work in order to understand how the branching works. Okay, so let's first learn how these flags work and what things actually affect them apart from the compare command. And then it gets clear how this works within the compare command. So the very first flag to consider, so let's start with the negative flag. So for instance, I say to x, I want to load the value of 0, 0, which it is, and it is by default actually, and I just want to say decrement x. So if I assemble and run this in the debugger, what happens? The X register would wrap around, so it would turn to FF, but the negative flag would be set, giving us an idea that it just kind of like went below 0. So just loading 0 to X, and then we have this negative flag being set, and the value at the X register is wrapping around. So it's clear. Okay, so this is how we can see that this negative flag has been set. Then another example. So let's say we have 1 in dx and subtract 1. So in result, we'll have 0 in the register x. In this case, 0 flag would get affected. So let's see how that works. Okay, so step initializing x to value of 0, 1. In the next step, subtracting 1, like decrementing 1, and it has the value of, so the 0 flag has been set to 1. So I hope it's clear. And now the very last thing, so let's load the value, the biggest value possible to ff, and let's add with carry the value of 0, 1. Now what's going to be happening here? So first of all, we'll set the 0 flag because the value wraps around, so from ff it turns to 0. That hence the 0 flag is going to be set, but also it kind of overflows, like it's not overflows, it just exhausts the size of exhausts the bits that can be stored within the 8-bit register, and hence the carry flag is going to get set. So if we just run into this as well, we have a equals to ff, and the next step we have carry flag is being set and 0 flag is being set as well. So this are the very basics on how the kind of like rotating the values, like how the wrapping of the values in the registers back and forth, like to the plausible and then back to the negative direction, like from 0 to ff and from ff to 0, how this affects the 0 flag, the carry flag, and the negative flag. So in every case it just goes a little bit different. So just to give a general idea regarding the flags. By the way, the rest of flags, V stands for overflow flag. This one is called a reserved flag. I have no idea how this works and why is this needed. It seems like always the same. B is the break flag, which in this environment is always set to 1, and it's not clear whether it's possible actually to do something to this. Now this one is interesting. So decimal, which is responsible for packing decimal digits, and this is going to be covered a little bit later within this tutorial, right? The interrupt flag also. I don't know where exactly we can use it. So in this particular environment, it doesn't really seem to be necessarily needed. However, this 0 flag, carry flag, and the negative flag are really useful for, especially for the compare command, which affects them, and hence for branching. Okay, so now let's try to write a simple branching here. So let's say we load the value of let's say hexadecimal 10 to the A register, and I want to compare. So compare is the A register. If this was X, I would say CPX. If this was Y, I would say CPY. Okay, but let's stick to A. So just compare. So was that correct? Yeah, compare CPX, CPY. Okay, with let's say this 10. Okay, so in this case, I want to say, for instance, branch equals to, and let's say let's create a label equals, and here the label not equals, and just to make sure that it kind of works, we just increment the memory, the first memory address by 1, and then break, so we're no longer going after. And here we just here let's say we increment the second one. Okay, and break. So sorry, yeah, now let's assemble and start with the debugger. So loading the value of 10 to the A register, comparing. Now you see that this flags has been set, so 0 flag because has been set because 10 minus 10 is equal to 0. Okay, I'm not sure why the carry flag is set here, to be honest, but anyway, this is already enough to make the branch equals know that they are actually equal. So the ways that's stated something for branch equals, for instance, on equal, no, just branch on equal, branch on not equal. Yeah, so probably relying on the zero flag underneath, but I can't say for sure, so not going to be stating that. Okay, so the next step, all right, branch to equals, and then it now should increment the first element because it is yeah. So the yeah, let's see again. I just want to inspect. We can see how the program counter is different. So B, C, well, hold on a sec. Assemble, okay. Assemble and debugger, yeah. So 600 hexadecimal, yeah, so goes here, okay. Then goes here, okay, and then, yeah, then it just goes one step further on here. So, well, actually, let's make this goes after, so we can see that the program counter has jumped over a specific place. Just a better way to think. So 1, 2, yeah, and now from 4 it just jumped to here to 9, okay, and the next step it increments 1, so we know that the program counter has jumped because it is equal, because 10 is equal to what we have in in A register. It jumps here to equals and then stops. And now let's say here we can have let's say 9, assemble, okay, and run. And in this case, yeah, it's already done, okay. Let's start with the debugger. So load intent to A register, comparing. And now it's not equals. Hence, it's gonna be stepping forward. So now the program counter gets incremented by 2. So it goes here, which is not equals, and it would increment the second value in the memory here, step, and then it's not going anywhere. Well, actually, for some reason it still increments the pointer, but well, at very least, it doesn't make anything. Well, we can just make sure we can jump to not equals, and in this case, it's just gonna be changing the value and wrapping around. So that's pretty much all about it. Okay, and another interesting thing that I think it's worth mentioning is we just go back to the compare command. So how can we find things like if not just equals or not equals, or let's say greater equals. So if the value in the accumulator is equal or greater than the compared value, then the carry flag will be set. Yeah, and this is, yeah, by the way, yeah, this is the way why the carry flag has been set. So instead of using branch equals, instead of using the branch equals here, we can just use BCS, so branch on carry set. So in this case, this would be like jump if the value is greater, if the value of the A register is greater than, and greater or equals than the one that we're comparing with. So diving into the details of how exactly the flags are being set, and depending on what do you want to do in particular, you may find the proper branching instruction that is going to be fitting your needs. Okay, now let's have a look what I've been promising you guys to. Let's have a look at the backed decimal numbers, binary coded decimal, or just backed decimal. So we have a specific flag here, this D flag, and we have two instructions. It's not related to branching, it's more like related to this specific flag. And as far as I don't even know whether this flag exists in x86 architecture or not, but it exists in 6502, and I believe it's very specific to that. So we have two commands, CLD, let me just find that, CLD and SED. Yeah, so clear the decimal flag and set the decimal flag. And depending on this, we will have a different ways of how the add and subtract is gonna be. So by setting or clearing this decimal flag, the way of how the add with carry or subtract with carry is gonna be working is gonna be different. And in the real 6502 source code, you might be encountering quite often that it actually starts from CLD, clearing the decimal flag. However, in this environment, the decimal flag is by default equal to 0, hence there is no specific need for doing that. But again, like in the real world 6502 assembly code, this is encountered very, very often. So I just want to demonstrate the difference, and to be honest, I have no idea what's the practical application of this, but it just gets a little bit confusing if you don't understand it. So I just want to demonstrate this. For me, it's kind of a bit of a phenomenon, right? So how this works, and then you'll just see this by your own eyes and hope that gets clear. So when the decimal flag is set to 0, which is the default for this environment, the addition goes in its normal way, and we have, let's say just L to DA, which is to A register will load. Well, let's say, for instance, like FA, for instance, and then we want to add with carry. We want to add, let's say 1, just 1. And assemble and run, and the result is FB, which is very predictable, right? Because FA plus 1 is going to be FB, so in hexadecimal, that's how it is basically. So just to give you an idea how this looks in binary, just to give you a bit better understanding. So this is F, this is A plus 0, 0, 0, 0, 0, 0, 0, 1, and this turns into F and B. So we add in this byte here, this bit here, right? And we have this value of FB. So this is like the most natural way of just normal addition, and same stands for subtraction as well. But if we use the SED here and assemble and run, then okay, just need to get rid of this. Assemble and run. Here we have this decimal flag being set, and you might wonder what the heck is this value and where it actually comes from, right? So it might be a very, very like unclear of how this actually kind of works. So this is what is known as binary coded decimal, and the idea is that each of the 2 nibbles of each byte represents a decimal digit. To be honest, I don't clearly understand this like entirely, but I still want to share what I've learned so far about this. So let's say that we have the number that is beyond 10, or even, yeah, when the result of addition would be beyond 10. So let's say we have 8 here, and we want to add with carry 0, 1. So now we set clear the decimal flag, assemble and run, and we have the value of 9. And even if we set the decimal flag, we still have 9, right? So just make sure we still have that. Yes, we do. So we have 9. And now let's go for a different experiment. So let's just add 0, just to see how the decimal flag affects the initial number without any operations, just to focus on the decimal flag on its own. So here we still have 8 without any changes. So from 1 and up to 9, it's not and yeah, so if this is cleared, so let's say A, assemble run, so this is going to be A, B, and so on, right? However, if we set the decimal flag, then from 1 and up to 0, it's going to be exactly the same, right? But when it starts from A, then suddenly you see like what it does. It says that it's equal to 10. So it encodes A, right? It encodes A to a decimal value of 10. So we have so when this flag is set, then this hexadecimal value turns into the decimal value. So like it's binary coded decimal. Okay, so it's literally what is stated here. So it's, for me personally, it's a bit difficult to wrap around my mind around this. So if we have B, then we have 11, and up to F, here we'll have 16. But what is interesting then, that if we do this not with the least significant nibble, but with the most significant one, let's say like here, A, then here we still have 0. In B, here we still have 1, and in F we'll have 5. So there is not enough place to put 1 here, and well, as I understand, it just gets dropped, and it just uses this like what goes after after this 1 in decimals. So for 10 it's 0, for 11 it's 1, for 12 it's 2, for 13 it's 3, 14 4, 15 5, and that's pretty much all about it. So I'm not sure how useful this might be or why to use this. So if anyone of you guys much smarter than I am, if you know why this is needed, how this can be used for, how can this be applied in the real world applications, then please kindly let me know, because I didn't really manage to find the information why this can be useful actually. Okay, so I think this is it regarding the decimal flag. So just to avoid this weird behavior, because in most cases I believe that most programs you won't need that, so you just need to start the program with CLD. So clear this decimal bit, decimal flag, and just assemble run, and the arithmetic operations would just get normally in 16-bit mode how they needs to be. Okay, so what else? We are almost done. Yeah, so function calls and bytes declarations, and we're done. So function calls, I've been explaining how this works from the stack pointer perspective in the previous video, and now let's have a look how the function calls work, how we can write one using the commands. So for instance, let's say, so there is a jump subroutine, I believe, GSR, yeah, jump to subroutine, yeah, and yeah, I think we can just use JSR, and let's say function, so just the label, and here we have the function. For instance, let's say like whatever, LDA, like 01 STA to the first pixel, and then to return RTS, I believe. RTS, yes, return from subroutine. All right, so RTS, return from subroutine. And now here, let's make just an infinite loop, just to make sure that you'll now understand what I mean. And jump to loop, assemble, and let's use the debugger. So the program counter points here to the first instruction, and then it jumps over these guys and starts pointing here. So the next step, so now we are, so the address from where we've jumped to was pushed to the stack, hence the stack pointer has been decremented. So let's have a look at this one more time. So initially, here's where the stack pointer is. Okay, so the very first, so we call in the instruction. So what happens under the hood? So the program counter, address gets pushed into the stack, and then the stack gets decremented by 1, and then we gonna jump the program counter into the function territory. Here we're gonna be executing the instructions until return. So executing the first instruction, loading 1 to a register, executing the second one, putting this symbol on, putting this pixel on display, and then we go back. So when this fires, what would happen? It would first increment the stack pointer, and then it would fetch automatically. It would fetch the program counter's address, which was stored and which points here. So it would be pointing here then. So step, and you see like now program counter is equal to 3. The next step, it's always pointing to 3 because we make processors stuck in the infinite loop. So this is how it works. So pretty simple, and I believe self-explanatory. So I believe this is similar to most assembly languages, to most architectures. Well, at least in x86 it works exactly the same way. Okay, so well, I think this is all we need for actually getting started with programming something useful, something real, using this environment. And the very last practical thing that we want to have a look at is, it's not the part of the instruction set, it's just the feature of the assembly language, which might be different from one assembly to another, and most likely the way how it's implemented here is going to be different in like different assemblers. But I just want to demonstrate the concept. So let's inspect the memory location where the program counter starts with the 0600, 0600, and this it's probably better to call it directive, or maybe. So this is just the assembler command. So DCB, well, I'm not sure what it stands for. I believe this is declare byte or something like that. And we can declare bytes directly in hexadecimal. So let's say FF. I'm not sure, can we actually, yeah, probably we can do it like so. Let's say AA and let's say EE, assemble. And hold on a sec, run, yeah, just updated the monitor. So after we run what we have, so wherever the program counter is pointing to, we kind of like storing the variables to the specific memory cell. So if we have some logic before, some loading some value to a register, yes, I'm doing something useful there, assemble and run, so what, known opcode, excuse me, so I just don't understand. So it just says that it assembles. Oh, it just unknown byte, yeah, because we don't really need to go there. So let's stuck in the loop as well, and jump to the loop. So let's say this is our game loop, right? And this, in here we have the variables been stored. So yeah, now we have our program here. So here is the program that does something, right? And here we have the variables that we've stored to actually work with. Okay guys, so this is it from my side in regards to this tutorial. So I hope you've learned something useful, and I really hope that you get an idea of how to keep learning the 6502 assembly, how to use the documentation, and how to wrap your mind around all of the things, just to figure out like bringing things together in order to make it work. I know this wasn't very impressive because we didn't actually write anything useful in there. Just tried to focus on the instructions, the addressing modes, and things like that. So if you like the video, probably in the next one or the several videos potentially, we may try to write actually something useful, and to see the output, trying to write some simple game, for instance, like the game of Snake or something like that, just to see how all of this knowledge that we've learned so far may be applied in the practical situation. So I hope that's clear, and this is it from my side, guys. Thanks for watching. Until the next time, and take care.